Today's topic is projectile motion, which you can also think of as two-dimensional freefall. Last time we talked about one-dimensional freefall, objects that were moving straight up or straight down under only the influence of gravity. What's different here is that instead of moving straight up and straight down, we'll take an object, here's a ball, and we'll launch it at some angle, call it theta naught, above the horizontal. It'll be launched at some speed, v naught, so that it follows this path. What we want to do here is look at the kinematics of this motion. There are three things in particular that I want to highlight here and talk about before we do some examples and problems. The first thing is to notice what the accelerations are. I'll write them down here and then we'll come back and talk about them in a minute. For an object in freefall, only gravity acts on it. There's no drag or air resistance or anything else, so the acceleration is only the acceleration due to gravity, which is the same as what we talked about last time in one-dimensional freefall. Ay, the acceleration in the vertical direction, is minus g, minus 9.8 meters per second squared. And importantly, there's no horizontal component of acceleration. As this ball is flying through the air, it's in free fall, and the only thing acting on it is gravity. So the acceleration, I'll draw it in red, is always directed straight down. Minus g straight down, minus g, everywhere so long as this thing is in free fall, the acceleration is the same. It's minus g straight down. No horizontal acceleration. The second thing to point out about projectile motion is that the horizontal and vertical components of the motion are independent. So I'll say x and y are independent. We'll come back and talk about that in a minute. The third thing is the shape of this path. I'll mention this briefly here and then say a little bit more about it later. So the path that this object follows is a parabola. I'll show you how to find that parabola and leave some of the details of the algebra up to you if you want to work it out. Alright, so let's come back and talk about these things. We know that ay is minus g and ax is 0. Given those two components of acceleration, we can write down the kinematic equations as they apply to a projectile, to an object in two-dimensional freefall. Let's write them down first for the x component, and then we'll write down the y component. The first equation tells us that Vx equals V naught x plus Ax times t. But Ax is 0, so this term disappears, and I can just back this up and not include it. That tells me now that the x component of velocity at any point along the projectile's flight is the same as the initial x component of velocity. Let me draw it over here. It looks like this. V naught x is this orange component here. And notice that it equals the hypotenuse, V naught, times cosine of theta, theta naught. Cosine because this orange side is adjacent to the angle. Now what this equation tells me is, so long as the projectile is in flight, the x component of velocity is always equal to that initial x component. So no matter where this thing is, it's always going to be moving sideways just as fast. All those orange vectors are sideways and they're the same length. The x component of velocity doesn't change. Alright, the second and third kinematic equations actually reduce to the same thing. The third one tells us that delta x is V naught x t plus 1/2 ax t squared. But again, ax is 0, so this term disappears, and all we have is delta x is V naught x times t. The horizontal displacement increases at a constant rate as time goes by. The fourth kinematic equation, the time-independent one, gives us nothing more than this one does. It just relates the squares. So really, in the horizontal direction, we only have these two equations. This one reminds us that because there's no horizontal acceleration, the x component of velocity never changes. It always equals v naught cosine theta naught. And the second one tells us how far sideways the projectile has moved as time goes by. For the vertical direction, we have the same four equations that we had last time. In the vertical, we know that Vy is V naught y minus gt. And I'll draw that component over here in green. It looks like this. So there it is. That is Vy. And, sorry, it's V naught y. The y component of velocity at time 0. And that's V naught sine of theta naught. Sine because this side is opposite the angle theta. All right, then the next two equations tell us about delta y, the vertical displacement. We have this one, and then this one, and then the time-independent one. Okay, so we have those four equations that tell us what's happening in the vertical direction. Those are our kinematic equations as they apply to two-dimensional freefall, to projectile motion. Now let's talk about the fact that x and y are independent. If I look at these two equations that tell me about what's happening in the sideways direction, you notice that there's no y's in them. The sideways motion has nothing to do with the vertical motion. And the same thing happens here. These four equations tell me what's happening in the vertical direction, how this thing is moving up and down, and there are no x's in here. Now, that's important because it tells me that the x and y components of the position and velocity are uncoupled. What's happening in the sideways direction has nothing to do with what's happening in the vertical direction. When we solve a two-dimensional freefall problem, a projectile motion problem, what we're really solving are two one-dimensional problems. We solve either the x or the y, and normally we learn something from solving that lets us solve the other one, but we solve them one at a time. Okay, so we will use the fact that x and y are independent to help us solve these problems. All right, I'm going to show you an animation in a minute to see how the position, velocity, and acceleration behave as an object is flying through the air. But let me first just quickly mention this parabola. If you want to know what the shape of this path is as the object moves through the air, what you need is y as a function of x. You need the vertical position as a function of the horizontal. This is the x direction. This is the y. So what you want to do is eliminate time from these equations. If you launch the object from the origin, then delta x is the same as x, and delta y is the same as y. If you solve this equation for t and plug it into this one, what you'll find is that y as a function of x is of the form a plus bx plus cx squared. And that's the shape of a parabola. So every projectile in two dimensions has a parabolic path. Okay, so those are three important things about projectile motion. Ay is minus g. There's no horizontal acceleration. That gives us this set of kinematic equations that describe the motion. It's important to remember that we can treat the x and y components of the motion independently. What's happening horizontally is independent of what's happening vertically, and vice versa. That's very useful when we're solving problems. And it's good to know that as a projectile is flying through the air, it traces out a parabolic path. A few lines of algebra will tell you what these constants a, b, and c are. Okay, let me show you an animation now so that we can see a projectile as it moves and observe the behavior. So here it is. I'm going to play this and then we'll talk about what we are seeing. So here's a projectile. It's going to go flying through the air. And as it moves, we see the displacements, We see the velocities and the accelerations. Let's look at the velocities first. I'll play this a couple times. Let's look first at the x component of velocity. I'll point it out. It's right here as it's moving. And notice that that never changes. That tells me that this projectile is just going to move sideways at a steady rate. Once you know v naught x, v naught times cosine of theta naught, the launch speed, times cosine of theta naught, that never changes. Vx is always equal to v naught x, to v naught cosine theta naught. And that's that horizontal arrow there, never changes. Now let's look at Vy, the y component of velocity. At launch, this thing is going to be moving up, so that component will start out positive, but gravity will act on it and it will change in the negative direction. So it'll get shorter, finally it'll go to 0 at the top, and then it'll go negative as it starts to fall. Let's watch it. Here it is positive, but see how it's getting shorter? It's not going up or down, and now it's going down, and it's going to speed up faster and faster in the downward direction. I'll play it again. Going up fast, but slowing down because the acceleration is down. No y component of velocity, and now there's an increasing y component. One other thing to point out about Vy. What we said last time about the y component of velocity having the same magnitude at a given displacement applies here also. If I pause this right after launch, the object is moving up at this speed. If I come across over here, it'll be moving down at the same rate. If we were to pause it here, it would be moving up at some rate. If we come straight across to the same vertical displacement, it'll be moving down at the same rate. So Vy squared over here would equal Vy squared over here. Let's play that and we can see it. Here it is going up at some rate. Let's wait till it gets back down over here. Now it's going to be going down at the same rate. At the very top, there'll be no y component of velocity. I'm going to try to pause it at the very top of the motion. And right there, I missed it by a little bit. Let me back it up. Right there, Vy is 0. No y component of velocity here. It's moving totally sideways. Right there, moving totally sideways. It's still accelerating. Acceleration is always down, but it's not moving up or down. All right. Notice the acceleration vector A is always directed straight down. Let's look at two more things, delta x and delta y. Delta x is the horizontal displacement. You might see a little vertical line here that's tracking the x component, and that just increases at a steady rate. That's our delta x equals v naught x times t. Delta y behaves exactly like delta y did for our one-dimensional free fall motion last time. It goes up as the object rises. It reaches the maximum where Vy equals 0, and then it starts to fall. All right, so hopefully that animation gives you a feel for how these parameters are changing or staying constant as the projectile moves. I want to do a couple of examples now that will focus on some values of the velocity and displacements at key points along the path, and then we'll look at some problems.